computer. Okay. 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 Welcome everybody to this junior seminar. It is a pleasure for me to introduce Alessandro Violini, a PhD student in Basel. And today's talk is about instability for inhomogeneous Euler equations.
Thank you. I'm very happy to be here. And I will start from the basic. So if you want to model a fluid, usually you use Navier-Stokes for one fluid. If you want to that this fluid is also incompressible, you use homogeneous incompressible Navier-Stokes, which is the following system. So let me start. The first PD is the Newton's law, is the equation for the velocity field. The second equation is the incompressibility condition, and then you have the initial data, which is given. So the two unknowns are the vector field, the velocity vector field, which is in RD with x value in RD, and then the pressure, which is a scalar quantity. And then the viscosity, V or nu, is fixed, and it is strictly positive. Since probably for some of you is the first time seeing this PD, let me go term by term. So the time derivative is quite easy. And then the first critical term is this nonlinearity, which has this form. So let me say first that U tensor U is a matrix, since U is a vector. And this matrix has a ij component, which is ui times uj. And the divergence of a matrix is a vector. And this vector has a I component, the divergence of the ith row. So if I want to compute this, I go with Einstein notation. I compute the j derivative of the ui uj, because it's the ij component of this matrix. Then I can use the product rule. I get these two terms. And the second one is 0 because I'm divergence free. And this partial j uj is 0. And so I can write this term, since I'm incompressible, in this way, which is quite common in fluid dynamics. The second term is the gradient of the pressure. And let me say that the pressure is not really an unknown of the problem, because for fixed time, t, if I apply the divergence to my Newton's law, the first term is 0 because it's divergence free, and I can commute the time derivative with the divergence. The second term becomes this one. The divergence of the gradient of the pressure is minus the Laplacian on the right hand side. And the divergence of the Laplacian of U is 0 because I can commute the Laplacian and the divergence. And first, the last term is simply this one. And this is there just to model the friction between the particles. So I have the unknowns from the velocity field, one unknown from the pressure, which is not really an unknown because it's completely driven from the velocity field. And I have d+1 equations because this is 1 and this is a vectorial identity. The first computation you do with Navier-Stokes usually is to find the energy balance. With energy, I mean the L2 norm of the velocity square. Since the density is constant, you can assume it's 1 because I'm modeling just one fluid. So how to get the energy balance? You pick the Newton's law and you multiply it with the U, with the velocity field, and you integrate in RD. So you get the following expression, right, which is quite clear. And then you have to go term by term. The first term, you just use the product rule, the inverse of the product rule. So the time term just becomes this one. So the derivative of the energy. The nonlinear term, the pressure term, is quite tricky because you start from this, which is the third term there. You add this part, which is 0, because the divergence of U is 0. And then you can use the chain rule, the inverse of the chain rule here, to write this sum as this. And then the integral of a divergence is always 0. You can do the same with the nonlinear term if the velocity is regular, because you get this. So this is your nonlinear term, which is now cubic. And you write this as this by the inverse of the product rule. Then you can add this, which is 0, because it's divergence free. And then you can use, again, the inverse of the composition to write this sum as this, and this is 0, because it's the integral of a divergence. So you are left with the last term, the viscous term, and in this case, I just use integration by parts. So I write the Laplacian of U scalar U as the gradient of U. Double dot I mean that I'm multiplying the ij component of the matrix times the ij component of the other matrix. And so I get the last term. So if I collect everything, I just get this balance, which is quite easy. And then I can integrate between time 0 and time s. And the first term becomes the US energy, the energy at time s, minus the energy at time 0, which is on the right-hand side. And then the integral of the viscous term is this one. So the first thing we can say is that if U is regular, the only reason why I dissipated the energy is due to the friction, to this term. So this term is the only responsible for the dissipation of the energy, which makes sense because since I have a friction, I should dissipate. Now, if I assume that this friction is 0, the previous system becomes the Euler equation, homogeneous incompressible Euler. That's why I write HE, because it's homogeneous. With the homogeneous, I mean that this is just one fluid. And as we have seen before, in the regular case, the energy is conserved, because I can do the previous computations, and since the viscosity is 0, I just get the energy conservation from this one. So since this is 0, I just get that this is equal to this, if the velocity field is regular. If the velocity field is not regular, maybe I cannot do the computation I did before. And in this case, maybe the energy balance, the energy equality is not longer valid. And in this case, we experience anomalous dissipation of energy. So you can dissipate the energy even if the viscosity is 0. So the problem is when we dissipate the energy. How regular is U in order to conserve the energy, and how regular is U in order to dissipate the energy? And this was a big problem in the last century. And the idea of Onsager in 1949 is to go back to the previous computation, and he recognized that the problematic term is this one, is the cubic term. Because here, just to write this term, you need that your velocity field at least is solved, because there is a gradient there. And so he started to ask himself when this term is well defined and when this term is not. His idea, which is just an idea, is to say, if I split equally the gradient between the three factors, I can write something like this, which is just an idea. And then he probably thought that the right-hand side here makes sense, is valid, when U is C alpha older, with alpha greater than 1/3. So we have just to think about the regularity in space. So his claim was, if my solution is C alpha older and alpha is strictly greater than 1/3, I will conserve the energy, because I can do the previous computation in some way. Of course, his proof was not a proof. Indeed, it takes the name of Onsager conjecture, which is famous fluid dynamics. So I fix alpha between 0 and 1. And if alpha is strictly greater than 1/3, any weak solution of Euler will conserve the energy. And if alpha is strictly less than 1/3, then there are weak solutions that will not conserve the energy. Notice that I'm not speaking about the Cauchy problem. Just I fix a functional space for the velocity, and I want to prove that the energy is conserved or not. The Onsager conjecture now is a theorem, because it was proved 6 years ago. The proof is divided in 2 steps. The first one is quite easy compared to the second one, because to prove that the weak solution conserves the energy, if you are more than C1/3 older, it's just a matter of commutator estimates, and this was proved by Konstantin Ititi in '94. And to prove that you can dissipate energy, that was more challenging. The problem is that you have to write down a solution that is dissipating energy in that functional space, which is hard. The first result on this sense were in '93 and '97 by Scheffer and Schneiderman. They produced the first examples of solution in LP, in L2 in particular. But these are far away from being alpha older. The first example of a continuous solution was written by Delelis and Sekkelidi in this range of years. And then there was, for like 10 years, a lot of improvement. So they start from a solution from a velocity field, which was just continuous. Then they managed to prove the alpha continuity with the exponent 1/7, then to exponent 1/5. And finally, in 2018, Phil Isaac managed to prove the work conjecture. And this was a breakthrough in fluid dynamics. So let me introduce another concept, which is the local energy. So if instead of multiplying by just U, I multiply by phi times U, and I do exactly the previous computations I did, I get this balance. Why it is different? The first term is clear, you have just phi, and then unfortunately, these two terms are not zero because I have the phi here. So I cannot use the trick I did before, that the integral on RT of a divergence is zero. And so locally, I have this estimate. Why I said locally? Because in some sense, since phi is compactly supported, I'm not saying that the whole energy is conserved, but I'm saying that in a small ball where phi is supported, the energy is conserved. And so by the previous computation, you can say that in a regular scenario for you, this local energy is zero in the sense of distributions by this equality. This is just this form written in a distributional sense. And now with the same structure of local energy, you can state the Onsager theorem. So if U is alpha older with alpha greater than 1/3, the dissipation is zero. And if alpha is strictly less than 1/3, you have dissipation. So what is the advantage to you, this dissipation? Is that if you prove that the dissipation is zero, is something better than just proving that the global energy is conserved, because you are proving that locally the energy is conserved, not just globally. And that's why this is slightly better. It's more complicated to work with this concept of energy, but it has its reason, I would say. Now, let me go back a little bit. And if I have more fluids, so 2 or more fluids, then I have a new unknown, which is the density. Density is a scalar quantity that is describing how much mass I have in one point at time t. And the inhomogeneous incompressible Euler takes this form. So the Newton's law is the same. I just have a rho here and a rho here. Then you have the incompressibility condition and this transport equation for the density. Of course, also the initial data now are two, the initial density and the initial velocity. In this case, the energy is given by this, which is mass times velocity squared over 2. And the dissipation distribution is the following, which is the previous one, just by putting rho here and rho here. You don't have to keep in mind the structure. Now, before going on, let me just give you an idea about what is this transport equation. So transport equation usually describes when you have a scalar quantity, which is transported by a velocity field. In this case, the velocity field is conserved, so it is slightly easier to study this transport. So a general transport equation is the following. So you have a fixed density, and you have your transport equation, and the vector field is incompressible. Having or not a well-posedness for this result is based mainly on the regularity of the vector field U. So if U is more regular, usually you have well-posedness, because your vector field is transporting everything in a smooth way. Indeed, you can say that if U is regular, you can write your solution in this way. This solution is called the Lagrangian solution, where rho at time tx is simply rho at time 0 composed with the inverse of the flow map at time tx, where the flow map is the solution of this ODE. Let me say that it's quite easy to see that if U, so the vector field is Lipschitz, you have existence for this system by the classical Cauchy-Lipschitz theorem. And so you can say that you have also this kind of solution. There was an improvement of this theory by Diperna and Dion in '89, where they proved that under some Sobolev exponents, you have the same. So if U is Sobolev, you have existence and the uniqueness of this type of solutions. And there was the last improvement, which is the Ambrosius one, that if U is BV, you have the same. So if your vector field is BV, you have a flow map in some sense, in a very weak sense, and you have still a structure like this. And this will be crucial. Now I will give you an example of the previous model. So fix a square in R2, and I consider the inhomogeneous incompressible Euler with a force, which is the gravity force. So the gravity force acting on the second component. And I'm using as initial data the following. So the initial velocity is 0, and the initial density takes two constant values, positive fixed, rho plus over and the rho minus on the top and on the bottom. And as you can imagine, this situation, this solution is stationary. So you can show that it will remain like this as the time runs. But if you think about the blue part as water and the yellow part as oil, what you would expect is that the water will try to go down and the oil to go up. But since this interface is completely flat, this model is unphysical, and the water cannot find the space to go down and the oil to go up. But as soon as you perturb a little bit this interface, then the water will find the space to go down. And this is a very strong instability, because this interface is unstable. As soon as you slightly perturb it, you lose completely the geometry. And this instability is called the Rayleigh-Taylor. And this is the classical picture from Wikipedia. So I'm starting with the heavier fluid on the top and the lighter fluid on the bottom. So the water and the oil. And for small times, probably you have still a regular evolution like this. But as soon as the time will get bigger and bigger, you lose completely the geometry. Really, this is a very hard problem to study, because you have more or less every problem you can have. So you have a non-uniqueness, there is this turbulence, you can study the stability or even the geometry of this mixing zone. And from the physical point of view, this was well known in the last century. From the mathematical point of view, it was very hard to approach. But 4 years ago, there was this article by Gebhard, Kulumban, and Security, where they started to prove this, and they managed to prove a non-uniqueness of the previous configuration. But I would like to point out this sentence from their introduction in their article, where they write that the problem of this case, so since the density is not constant, because we have two positive constants, you could have two problems. One is intrinsic in Euler, so it's the Onsager case. So you can lose energy because the velocity field is not regular. And the second one is that you can lose energy because the density is mixing. Because if I go here, probably here I'm losing energy, because the density is very, very mixed. Now, it's very hard to give a proof of this. Let me first say that when I say turbulence, I mean anomalous dissipation. So turbulence for me in this talk means that I'm losing energy in a strange way that I cannot explain. And for the same reason, turbulence means that the local distribution is positive. So I'm dissipating energy somewhere in my domain. So the problem now should be to understand if these two mechanisms are linked or not. So is it possible that I'm losing energy just because the density is mixing, or the energy is just lost because of the intrinsic structure of Euler? In some sense, what I'm saying is, let me go back here. Clearly, I can lose energy even here in a small ball here by the structure of Euler, because maybe there the velocity field is very non-regular. But probably what I would like to prove is that I'm losing energy here in the interface, because the behavior is quite chaotic. To prove this, you need to go with a very clever functional setup. Let me first recall that this is the dissipation, where I have added a force since I have the gravity force, but you can forget about it. And as I said before, proving that the distribution is positive in this case is very, very better than just prove that the global energy is conserved. Because if you prove that the global energy is conserved, you don't know where maybe the energy is just moving in the domain. And if you prove that the global energy is lost, so you are dissipating the global energy, you can't know if your dissipation is due to the mixing of the velocity field or of the density. While if I can prove that the dissipation is due to the local energy, so you have a local dissipation of energy, then maybe you can prove where you are dissipating energy in your domain. And your final goal would be to prove that there is a functional scenario where I'm dissipating the local energy in the mixing zone. And this will be my result, more or less. So first, so the goal is I would like to find a functional space for ρ and for u where I can prove my claim here of the previous page. So first, I will pick x, the functional space for the velocity field, in such a way that the solution of a homogeneous Euler will conserve the energy. So I will put myself in a scenario where I do not lose energy due to the mixing of the velocity. I don't want to lose energy because the structure of Euler is very irregular. So I will pick a functional space for the velocity which is regular enough to stay in the positive case of the Onsager theorem. And then I will pick a functional space for the density y in a way that for u in x and ρ in y, I will lose the energy. So my local distribution of energy is strictly positive. In this way, in some sense, I'm proving that I'm dissipating energy due to the mixing of the density, because the velocity is in a regular enough space. So now we have to find a good candidate for x and a good candidate for y. The main problem will be to find a good candidate for x. So let me see some possible candidates. So first, you can think about picking x and y in as a very small spaces. Smaller, you can think about smooth functions. But in this case, clearly the dissipation is 0. But if your ρ and u are smooth, then you are not describing the previous experiment. Because if I go on the picture here, clearly here the density is not smooth. You have a jump between yellow and blue. There are two values, and even here probably is even more chaotic than two values. So if you put yourself in a scenario which is too regular, of course you don't dissipate the energy, but you are not describing the physics behind. And so picking something like this is not good for our goal. So you can think, okay, so let's pick x order regular with alpha slightly better than 1/3. So I will conserve the energy for Onsager theorem, but it's not a lot of regular. The problem is that if your flow map is just older, if your velocity field, is alpha older, you don't have a flow map because you don't have enough regularities to really transport the velocity field. If your velocity to transport, your density. So if your velocity field is just older and not Lipschitz, you can immediately lose your regularity. And so it's very hard to work in this framework. And I'm not able to work in this setup. So you can think that x is Lipschitz, but if your x is Lipschitz, also the distance is preserved, and so it's very hard to allow ρ to mix. And so probably a mechanism and an experiment like the one before is not described by a velocity field which is Lipschitz. And so it turns out that a very good functional space for the velocity field is BD, because you have the existence of a flow map by the work of Ambrosio, and at the same time there was this work of Luigi and Marco from my group 2 years ago, where they managed to prove that the energy is conserved for Euler if you use BV. So in some sense, BV is a good space for the positive part for the Onsager conjecture. So x, so my velocity field will be in BV. And for a completely other reason, also the density will be in BV. But the density would just be in BV because since I will start from a fluid that will take just two values, so density rho minus and density rho plus, you have a jump. BV is a good space to model this. So there are two completely different reasons. And our result that I would like to first, yeah, that's true. I would like to give you an idea of BV functions just for completeness, which will be very basic. So a function is BV if the gradient is a random measure and the function is integrable. So the classical example of a BV function, which is not Sobolev, is the Heaviside function on the R line. So if x is positive, is 1, if x is negative, is 0. In this case, the gradient, the derivative is a direct delta in the origin. And you have that the total variation of the gradient of f is 1, because it's the length of the segment where you are jumping. For the same reason, if f is BV, I have not written here, so you are a characteristic function of a set, then the total variation of f is the perimeter of A. If f is in BV, I have not written here. You have also to require that f is. And this will be used later on, this basic fact. Another basic fact is that if your function is BV, then this gradient can be decomposed in three parts, and this is a general property for measures. So you have an absolutely continuous part, f, which is the regular part. You have this jump part as before, like in the Heaviside example, so the set where you are jumping. And then you have this counter part, which is simply everything else. Let me also say that for BV function, probably you know that the jump part is really concentrated on a hypersurface. And so you can say that the counterpart is the part that is not concentrated on any hypersurface and not even on an open set. Otherwise, it will be the absolutely continuous part. The classical example of a function with a counterpart is the following one, the counter staircase. You can prove that this function has a counterpart because the total variation of this function is 1, because it's going up for a segment of length 1, and it is constant almost everywhere, by h1 almost everywhere. And so you can h1 almost everywhere. And so the absolutely continuous part doesn't give you a contribution to go up, because it's constant. Clearly, you are not jumping because you are continuous, so there should be a counterpart. Last comment on this very basic slide on BV function is that the BV function and C alpha order function are completely different. You can find BV functions that are not C alpha order, like the Heaviside, but also the opposite one, like the Weierstrass function. So if you are going up and down too many times, you are alpha order, but you are not. So they are completely different classes from this point of view. What is magical for BV function is that you have a flow map, even if you have a structure like this, which is quite crazy. My main theorem that I have proved with my colleague Marco is the following one. So if you are BV, now I'm also putting the time regularity, of course, and also bounded, because I don't want the density to explode. Then the dissipation D is a measure, so not only a distribution, but a measure, and it is concentrated on the counterpart of the gradient of the density. Okay, how to get such a result? First, let me explain what is the meaning of this result on the previous example. So consider this initial datum. So I'm starting from a slightly perturbed interface. So the water is A plus and the oil is A minus. Since I have a flow map, because the U is in BB, this regular initial data will be transported like this. So A plus is transported by U, the flow of U. And the same for A minus is transported by the flow of U. And what is nice about having a flow map is that clearly here I don't have a counterpart, because I have just a jump on the density. And also here I don't have a counterpart, because I have still a jump. Maybe this jump is very, very bad, but it's still a jump. So if I start from something since rho 0 has no counterpart, also rho t will not have counterpart. And so we can say that if I apply my theorem, in this case, I will conserve the energy, so I don't have dissipation, because I don't have a counterpart for the rho. So the only reason why I cannot apply my theorem to this example is because rho t is no longer in BD, because I'm not sure that this function is BD for fixed time t, because maybe the case is that the interface, so the hypersurface where I'm jumping, is too long. And this is probably indeed the case. So the reason why I have dissipation on the previous experiment is because the length of the interface is exploding. So if I go back in the picture, is this one, okay? Probably until the length of my interface is finite, I'm BV, and so I'm not dissipating the energy if U is BV. But as soon as my interface is getting infinite, which is probably the case here because the H1 measure of this curve is probably infinite, I'm dissipating the energy. So this was an example where to apply our result, which is completely general in this case. So you can use it as soon as you have a solution of inhomogeneous incompressible Euler. But now, yes. Yes.
So you mean that the dissipation is not allowed until
These
the
are
counterpart, right?
Yeah.
So, and now you said probably in the physical case, what happens is that the length of the interface, say, mixed region, is infinite. The area is infinite.
Yes.
So you are outside of BV.
Yes.
But is it not possible that maybe there is a counterpart that is created in this process?
Because and not because you have a flow map. If you have BV for you,
okay.
this is
Yeah, you mentioned that.
you cannot develop a counterpart if U is BV clearly. This is everything a priori. I'm not solving a Cauchy problem, unfortunately. So let me just give you a basic idea how to prove such a theorem, which is quite long, but I will try to be short. So first, you pick your weak formulation, and instead of using as a test function phi u, I use this function, which is a sort of phi u because it is proportional to phi u, but I'm adding rho u modifying in space and dividing by rho epsilon. The reason why I use this test function is because it allows me to do more computation in a low regularity framework. So you can pick this function, you can put this psi here, and you can go on with the computation, a couple of pages, and you will reach something like this. So your local energy, your dissipation, in the sense of distribution, is equal to a remainder, where this limit is has to be intended as a limit in the sense of distribution. So you can prove, if you allow just U and rho to be L infinity, to arrive at something like this. So your dissipation is equal to the limit of a remainder of an error. Clearly, if rho and U are smooth, this error is zero. It's quite easy to show. I cannot give you the full expression of R epsilon because it's very long. And now the goal is to estimate this R epsilon, changing our regularity framework. So let me say that R epsilon can be split in two parts, D epsilon and B epsilon. D epsilon is more density based, and you can prove that if rho is Sobolev, which is not a good framework because you cannot even allow jumps. So in our model it's not good, but the dissipation is zero. And if rho is BB, you can prove something like this. So the first term is really concentrated not on the counterpart, on the full singular part. So on the jump part plus the counterpart. And here you can prove by using some regularity, some theory of BB functions in BB. And you can prove an estimate like this uniformly in epsilon. And then you can start to work with the second term. The second term, V epsilon, is more velocity based. So the first term just matters more or less the regularity of the density. For the second term, what matters is the regularity of U. And you get this very long commutator in our case. And if you are not regular, you can prove that this will converge to zero. It's a commutator. Unfortunately, here I cannot show you how to work with this because it's too long. But let me say that we have taken our idea from a work of Ambrosio, from Alberti Ambrosio, where they were working with the following commutator, which maybe is more famous. This is the commutator taken from the transport equation. So you have this C epsilon, which is just this. Clearly, if rho and U are smoother, this will converge to zero. But if they are not, it's more tricky. To work with this commutator, so let me read it. First, you are modifying rho times U, and then you are subtracting just the modification of ρ. And so you would like to study this C epsilon and this convergence in L1. What is the strategy? First, you pick a modification kernel, eta, and you expand the full modification. So the L1 norm will be exactly like this. I'm just using the definition of the modification. So in the first term, I'm modifying ρ and u, so I have the increment on both sides. And on the second term, I have just the increment of ρ because I'm modifying just ρ. So I'm just writing the definition of the modification. Then what you do, you can merge some terms, you can collect some terms, because I'm collecting the modification kernel, ρ, since it is modifying in both sides, and then I have the increment in u. What to do now, you simply cut away the ρ, because ρ is bounded, you don't want to study ρ, and you arrive at this term in L1 for every q compact in LD can be bounded up to a constant, which is not important, by something like this. And let me call this C epsilon prime. If u is Sobolev, this term in L1 will converge to this gradient times the increment y. Epsilon, and the epsilon of the increment will be simplified from the epsilon in the denominator. And so this term will converge it to something like this, and this is 0 by odd symmetry. Because the modification kernel, you have to pick it in a good way, but usually is even, and usually is even, especially the gradient of a modification kernel is even. And the y is odd, this is a ball, and this is 0. And this idea was used by Di Perna and Lyon in 1989 to prove that if you are Sobolev, which is exactly what they do for the flow map, this commutator will converge to 0. If u is just BV, this will not converge to 0. You don't have enough structure to do a proof like this. But fortunately, there was a very important technique by Alberti Ambrosio called Alberti Ambrosio optimization kernel, which is the following. You consider, again, let me go here to this, and you pass to the lim sup in epsilon, and you get something like this. So let's focus on the first one. So what is the difference from the Sobolev case? That now I'm just measuring q, because this is a measure, so I cannot really write an integral. So I'm writing this, I'm not very precise, I'm just skipping some steps, but you get something like this. Then you use Radon-Nikodym decomposition, and you write your measure here. This is your measure substance, because y is another variable, as a density times the total variation measure. Density will be mx, which is a matrix, because the gradient of u is a matrix. And now you put here, instead of u, this expression. And then you can change the integral between y and the total variation, and you get this expression. And now what is crazy is that Alberti, he has studied deeply this integral here. And in his work, and also in Ambrosio's work, what they do is the following. Since in my problem, I have proved that I have this distribution equal to a limit of an error. I have proved that the other term of my error can be bounded by a quantity that does not depend on epsilon. So only this term is depending on epsilon. I can do the infimum along my modification kernel. Okay, and now there exists a sequence of this modification kernel. So not an optimal modification kernel, but a sequence. And this sequence is very well defined in order to balance out the structure of this rank 1 structure, because BV function they have a rank 1 gradient. And so you can find a very particular sequence of modification kernel in order that this, for y fixed, this is a completely general statement, is equal to the trace of this matrix. So you can put here every matrix. So if you try to compute this, you will discover that by Alberti's lemma, this is equal to the trace of mx. And then trace of mx you can prove by a simple argument. It's simply the trace of the gradient of ux, more or less. And the trace of the gradient is the divergence, and so it's 0. And so you can prove by using Alberti Ambrosio optimization kernel that C epsilon prime is not converging to 0, but the infimum is. And so you can pass the infimum on the left and on the right, and you will prove the following, that your dissipation is concentrated on the jump part of rho and on the counterpart of rho. Now, I have no time, of course, but the second part of our work is to prove this theorem, which is slightly more technical, because the previous one I just taken from Alberti Ambrosio, is that if rho up, if the dissipation is a finite measure, which is the case if they are BV, and they have a trace, which is the case if they are BV, then the dissipation measure is not measuring hypersurfaces, any hypersurfaces. And since the jump part of the gradient of rho is concentrated on hypersurfaces, I will not measure that hypersurface. And in this case, you can get this result. So it's really concentrated on the counterpart of rho. Also, I have skipped some details, but this was the work I did with Marco. Thank you.
Maybe the commutator
Estimates
they use are the same that, for example, are used to define the Rayleigh solutions. Because there's a way that you.
Yeah, but you mean which commutator? This one?
CVD, yeah, you solve the CVD, but with something that is modified with this cadence, and then you tend the parameter to 0 and find
a commutator.
You have to make some commutator.
Yes, no, it's not this one. This one is just from transportation. This is just a big. This is transfer equation, you can modify it. You would like to write something like this?
Yes, for the continuity.
Yeah, you would like to write something like this. Yes. So if I modify in space this, if I no, the problem is that if you work with Navier-Stokes, you cannot get a commutator, which is just a linear. It should be at least you have some problem with U times U.
It was not a commutator on
the transport. No linear term, and probably on the no linear term, which is probably something like this. Now it depends on the.
It was in the nonlinear.
Yeah, would be probably a commutator. And this is slightly different from the Bereops one, because here, since I'm using this local energy, I'm multiplying by U, so I have this cubic structure in U. So this is a cubic commutator in U. But you can just mainly, if you write the expression of this, expanding eta, so like this, you will recognize that more or less we have really the same structure of Alberti and Ambrosio. And then you can do the same proof because also U is in an infinity. Yes, let's see.
Maybe I have some questions. You say dissipation of energy. It means that the energy decreases, right? Cannot increase.
And this is a very good question.
Because if you invert time, for instance.
No. The problem is the following. From if you pick Euler equation with the viscosity equal to 0, it can increase. And you can prove by convex integration. In a very low regularity framework, the energy can increase. So you can start from a dead system and to recover a system, which is quite crazy. But if you study Euler as a viscosity limit of Navier-Stokes, you can do the Navier-Stokes and get the energy balance, which I did on the second slide, I think. Yes? And now if you do the limit of eta, maybe this is not 0, because you have the viscous term, but maybe also U is depending on the choice here, because I'm solving for fixed viscosity. But so maybe this term will not converge to 0, but it will be positive. because this is positive and this is positive. So in that case, you can only dissipate. But if you take Euler just as a system of PD, you can dissipate energy. Yeah, the energy, sorry, you can also increase the energy. While for vanishing viscosity limit of Navier-Stokes, you cannot. So it's not really physical, consider.
Because from this equation, it's clear that the derivative is negative. If you don't have this.
So if you do the computation, you don't know from Euler. But from Navier-Stokes to Euler, you will get, I mean, this is negative.
It is negative.
So also the limit will be negative. Yeah, that is a good question. Thank you.
Are there questions online? Maybe, maybe not.
No, it's okay by me.